Hello, good morning. It's kind of great to follow Pat and do a talk up here. So Pat's one of my heroes, and I worked with some people who worked with him. And it's kind of, we have so much great things in our industry, and we're starting to have to rediscover them, especially as we go into this kind of multi-everything world. And that's where kind of Tara and I started talking, Jonas and I started talking. It was all kind of great. And one of the subjects I'm passionate about is having systems respond. They need to respond to us in this nice, timely manner. Otherwise, they're not very good. They just don't give us what we need. And so many systems, we end up feeling like this when you deal with them. We get very frustrated, or even worse, they feel really badly. Often, when people are talking about these sorts of systems, they use the term real time. I want to quantify what I mean by real time, or just even qualify it. Now, real time, I want to talk about it as hard real time, and this is a very well understood and precise discipline. So this would be an example of a real-time system. This is called the goalkeeper. It's the last line of defense on a British warship. When everything else has failed to stop an incoming projectile, this has the job of stopping it at that last instant. So if you can imagine, at that last instant, and it's going to try to take out a missile, and it's going, shoot the missile down, garbage collect. Shoot the missile down, garbage collect. Which one's it going to want to do? Because if it doesn't do its job, it's a catastrophic failure. There is no maybe, probabilistic, anything like that. It has to do the job, or it's a catastrophic failure. People die. That is true real time. And so you have to meet that guarantee, or we can't do it. Now, a space I work a lot in is I call soft real time. And this is typically things like financial systems, whereby if you don't meet your response time guarantee, bad things are going to happen. You're probably going to lose a lot of money, but people aren't going to die typically. So it's not the true real time as we see. Often, I keep hearing people talking about real time, and what they really mean is what I call squidgy real time. And this is our users that are frustrated using our systems. But the truth is, these days, given the computing power that we have, if people are designing websites or any interactive user application and the user has to wait, I consider that a major failure because it is so fast. If Google can index the entire web and respond sub-second, why do people in simple shopping sites take forever to respond, or trying to book a flight, or trying to book a hotel, or anything like that? It can take tens or even high tens of seconds to do this. This is just wrong, and we shouldn't be in that sort of case. Quite often why people are doing things wrongly in this case is they're unaware of what's going on. Many people go ahead and they start to build systems and they put off all of these qualities of service, which is a lot of what the Reactive Manifesto is about. It's about qualities of service. Are things responsive? Are they resilient? Like, will they behave how we need them to be? We need to think that way. Because most people are happily building their systems, they're digging along, and they don't know what they're about to dig into. This is kind of where I make a living, because people dig into that stuff and then they go, oh no, help, come sort me out. So a lot of what I'm going to talk about here today, I've got experience at the far end of close to real-time systems, or very, very responsive systems where we're dealing in microseconds, even sub-microsecond in some cases. So some of the patterns that I talk about, people go, that doesn't apply to me. Well, I've also worked on lots of booking sites and lots of other things, and I find that it's exactly the same algorithms and the same approaches that matter. It's all quite fractal. So if I give an example that's in tens of microseconds, the same approaches apply if it's tens of seconds or tens of milliseconds. It's all very similar. We have to learn to do the right things. And nature shows this so well. There's a lot we can learn from nature. And I think it comes down to a lot of our systems design. Being inspired by nature is a much better way of doing it than others. So what are we going to talk about today? Well, 5 things. I want to talk about how we measure our systems, because this is very important. I'm going to talk a little bit about the theory behind building responsive systems. So we've got some tools that we know how to use and how to sort of theorize about how our system is going to work. I'm going to talk about how to put that in practice with a real example. Then we'll go forward and talk about some of the pitfalls. Those little guys who are digging away underneath and they're about to dig under the latrine, how it goes wrong, what are those things that go wrong? And finally, I want to finish it up with some algorithms and techniques we can take away from this. So useful things to take home. So let's talk about how we record. First up, pro tip, record everything. I see quite often people sampling systems, and sampling systems hides far too much. It is possible to sample systems in ways, and you do capture most of what matters, but that actually requires quite a bit of thinking and being quite clever about it. Let's be simple rather than be clever in how we do things. So let's record everything. And there's ways we need to record it because sometimes that's an awful lot of data. Now, how do we record lots of data for responsive systems? Well, the best thing we can do is put it in a histogram. There's many good examples of histograms out there, but here's one from a trading system where we have captured the response time for any given request into a system. And look, you get an interesting distribution. Like over here is where our typical cases are. We're typically responding well less than a millisecond within the system, but we've got interesting things out here and out here. And this is a log scale. So we're starting to see lots of interesting things out here. People will often talk about the statistics behind this, and they use averages. And averages are a real problem in this space. And why is that? So let's take the first common way people use averages, and that's the mode. The mode is the most common and the most typical case you're going to see. That's interesting. So our mode is here. We're seeing a lot of that. That's interesting. Median, which is the middle of the range when you line everything up. Well, that's not really telling me anything interesting as a median. The worst one is the mean. The average, as most of us know it. What does that tell us about the performance of this system? It doesn't tell us what the typical cases are. It doesn't tell us what all this nasty stuff is out here. Don't use means. They really don't help you out. Let's take an example to put this in context. So let's say I've got a system. It's doing 1,000 transactions a second, and it typically has a mean response time of 50 micros when it's in normal usage. Now let's throw something into that to mix it up a little bit. Let's assume that once a second we're taking a GC pause, and that GC pause is 25 milliseconds. That is not uncommon for a young generation collection in a system that's generating a fair amount of garbage. What does that do now to our mean or our average response time? We have the typical case of 50 micros. We have these odd cases of 25. Well, what's interesting is when you have the 25 case, it's not just one instance of 25 as mean, because your system has stopped. You were injecting at 1 per millisecond before that. So you've got 1 at 25, 1 at 24, 1 at 23, 1 at 22, the whole way right down until you're back in sync again. So you've actually got a mean case there of 25 of them having the mean of 12.5. So that throws you off quite a lot. You apply that as your overall mean now. We've got 300 microseconds. That tells me nothing useful about the system. It's hidden the big pause, and it doesn't tell me the typical case. So let's not do this, because if you build systems and you start using means, and then you have to talk to real business users to explain what's going on, you end up feeling like this. It's just silly. It doesn't make any sense. Let's not do that. So let's forget about these means, forget about these averages, and we should be talking about percentiles, or quantile distributions is what's really interesting. So here's a slide that Gil Tenney loaned me. He's going to speak tomorrow, so I'm not going to talk too much on this subject. But this is a much better way to show the response time of your system. So we're looking across here of like, what are the 90%, the 99%, the 99.9? Sort of look at these and quantize them going like that. And so I can see how many duration points I've got up until that. And so I can see, well, right up here, my system is taking much longer to respond than it is down here. But we're getting this interesting of facts. The difference between these lines and these lines is that problem that I just mentioned where you took the GC pause and you didn't hit the hit of 1 at 25, you took another 1 at 24, another at 23. All of that problem is you omitted a lot of what was really going on in the response time of your system, and that has been coordinated with that event, and Gil names that coordinated omission. So that's something to be aware of. And wait for tomorrow. I'm sure Gil will talk a lot more about this. So the main thing is don't deceive yourself. Feynman talked really well about this and doing good science. So let's not deceive ourselves. Let's measure correctly and make sure we're measuring the right things. So now for measuring, let's put a bit of theory behind this and see what's going on. Well, typically, we start needing to know about queuing theory. Queuing theory is very key to knowing the response time of your system. And most people will be familiar with the J-curve. So as I increase my utilization on the system, my response time starts to increase. And that is because queues are forming. It's actually quite interesting because as you increase the utilization, the likelihood is when something arrives at the system, something is already being processed, so you form a queue. The higher the utilization, the higher the probability of that queue getting longer. And that's why you end up with this curve. Notice how it goes really bad after about the 60th percent. So if you have a highly utilized system, it will stop responding quite quickly. So we hear people talking about they want to increase the utilization of their systems. That's a really bad thing if you want the system to be responsive. You need some slack in your systems. This also applies to any system. Systems like developers writing code to deliver a project, that is a system. If you're a project manager and you want to go for high utilization, guess what? You're not going to have a team that's very responsive to the incoming requests that they have. You need some slack in that. So that's a curve. How do we end up calculating these curves? Like, how would I do that? Well, something to go look for is a thing called candle notation, and it's a nice way of describing the characteristics of a system. And you'll see a number of letters like that. So that last curve was actually described as an MD1, where the M, the first letter, is describing the arrival rate at the system. How that is characterized from arrival, that's a Markovian distribution, exponentially distributed. It's very unrealistic for a real system, but it makes the math simple for what I'm going to show you very shortly. The second letter, the D, is the characteristics of the service itself. I'll pick a service that's deterministic in its behavior. It could be Markovian, it could have other characteristics as well, but we want to design our systems to be deterministic because that's something we have control of. And the last part, the one, is there's one instance of that service. So if I had a cluster with many instances, I can then have a different profile to this. You'll see these systems described with those collections of letters. Based upon those collections of letters, you know what equation to pick to describe your system. So for an MD1, we get this equation. So I can work out what is my mean response time based on the service time and the utilization of the given system. And that will let me plot that curve. But one thing's really interesting is trying to work out what is the utilization. It's actually a function of the arrival rate and the service time itself. So this all becomes very self-circular. So you really want to keep utilization low. And here's a nice example. So going back to this curve, and this is something I find I can do quite a lot, the systems that get nice effects. So I've got a system that's running at 90% utilization. All of a sudden, like, I'm up here at nearly 10 times the normal response time you have in the system than whenever it's running low utilization. How do I make that system much, much faster? Well, I can make it typically 20x faster by making it 2 times faster for the service. Does that make any sense? You're probably thinking, what? How does that come about? Well, it's quite simple. If I'm up here on a 90% utilization and my service time is 1 unit of time, I cut that to a half a unit of time for the service time. What I've done is I've cut the utilization and I've taken that. So I've come down the curve from 90 to 45, then I've halved it again. Now all of a sudden I'm down here. By making the system twice as fast for the service, I made the thing much, much more responsive because I reduced utilization. And so these sort of things start to really matter. People keep saying, throw hardware at it, performance doesn't matter, all that sort of stuff. This is really hard to add later. Start thinking about it from the start and be able to characterize your system. So next pro tip is make sure you have sufficient capacity in your system, otherwise you won't be responsive. So how else can we speed up? Well, typically we can go parallel. That's the next way we can do it, because we can break the work down, we can go parallel. Many people will have heard of Amdahl's law here. Now, interesting, Amdahl wasn't trying to encourage people to write parallel systems. Quite the opposite. When he wrote the paper on Amdahl's argument, what he was trying to do was trying to scare people away from writing parallel code. And for very good reason. He wanted you to buy mainframes. He was peddling mainframes at this stage. So what's his argument? Well, basically, if we look at any given process, we can split it up into a number of components. Can we make any of those components go parallel? And if we can make them go parallel, we can get a speed up overall. So if I can parallelize part A, I can get a nice speed up on a 4-processor system. But let's say I can only make part B parallel, I can't get quite as good a speed up. So there's a clear thing here around what is the constraining component of your algorithm, what is the sequential constraint? And many algorithms have a sequential constraint. So let's look at what possible speedups we can get. So if 50% of my algorithm cannot be made go in parallel, the most I can get is a 2x speedup. That's the best I can achieve. Like, let's go out to the far extreme of, say, 95% of it can go parallel, but only 5% you can't. You still can't get more than a 20x speedup. In fact, you never get to 20x. You asymptotically approach it, but we never quite get there. So if we have algorithms that are got parts of it that can't be made parallel, we're just tied together. And this is all about where we have contention and we tangle and have coupling. We need our designs to be completely free of coupling if we want them to scale up and go parallel. It's really important to drive to some of these characteristics. But guess what? Amdahl had the best case scenario. The world's actually much worse than this. And Neil Gunther pointed out through some of his studies of systems that not only do you fail to reach what you want to get up to, it can actually go worse and get start to go down again. And this is because of coherence. So you've got the contention penalty, but you also need to make that data coherent at the end of the day. And you need to figure that into your equation. So this is universal scalability law. It covers everything that Amdahl covers, plus adds in the coherence penalty. And what does that look like when I start to plot that? Well, we've got our 5% of our algorithm that can't be made parallel, but I'll add in 150 microseconds of coherence delay to make that the data coherent that's contended. And guess what? I don't scale up. The red line, I start to actually get worse. So if I throw more CPU resource, more processes, more threads, whatever it happens to be at this, we slow down rather than speeding up. And these things are starting to become more and more common now as we get higher core count machines. That's what's for certain going to keep happening to us over the future years is we're not going to get much faster clock speeds, we're going to get many more cores, and we have to keep that data coherent if we're sharing it. We cannot be sharing data for this to happen, especially we cannot be sharing mutated state. We cannot mutate by multiple processes. So getting back to the queuing theory, and we had the MD1, well, that D thing, trying to be deterministic, we need to think about the service time. The service time becomes key to driving a lot of that. It becomes key to how we split things parallel, and it becomes key to our queuing theory. What we need to get back to in this is good old order of algorithms. We need to start thinking what are the order for algorithms, and we need to be going towards order 1 or log n, or some sort of algorithm that's over here. Once we're up here, this is not good. We will not be responsive as we throw load at our systems. Because if we go up with the products or customers or whatever interesting transaction volume we've got, we have to have the right order of these algorithms. So this stuff needs to be dusted off again. So let's say we dust off some of this theory and put it in practice. This is an example from a client I had earlier this year. They've kindly let me share some of the data, but I'm not allowed to name who they are, so hopefully I won't slip up and name them. So these people had a system, and it was a financial trading system. And they were doing thousands of transactions per second, and we wanted to capture what is the response time of the system. And so what we did is we done a scatter plot. And the scatter plot shows us what is the response time for every single transaction through that system. And it's kind of interesting. There's a clear sort of typical case, but there's loads of interesting behaviors. Like you got like the classic warm-up behavior over here, but there's these weird spikes, there's little gaps. This is all really fascinating, and it's interesting to dig into this stuff. And so first thing I want to do is I want to profile these systems. I want to get lots of logs from things like GC, from lock intention, all sorts of interesting things I want to find. And one of the things I found quite quickly on this system was they were using an old version of the disruptor. They were using version 2. The version 2 of the disruptor had problems where the algorithms were very coupled in the multi-producer case, and if one thread took an interrupt, it tied up lots of other threads in the system and caused some of this behavior, which is a real problem. So what we did is we upgraded to version 3 of the disruptor, which solved a number of these problems, and that's what happened after running the test again. So you just see, making a little change. And I think visually plotting all of this is really powerful. It lets you see a lot of what's going on, really helps understand. So we increased the mode case. So we were typically a good bit faster, and we smoothed out some of the effects. And then some of the other effects started to become more obvious. Like over here, we start noticing there's little step-ups in what's going on. And also this little jump. I find this sort of stuff fascinating. I want to know what that is. So what I want to do is zoom in on the chart to look at that little area. What does that look like? Well, this is fascinating because there's all this typical stuff here. There's a few sort of outliers, then boom, big jump up. Gaps with nothing happening. I want to find out what's going on there. So one of the great techniques you can do with things like Java is you can instrument the code. The bytecode, you can put other code in there to spot patterns and what's going on. And I like to do this a lot. Some of these patterns, once you see them a lot, you start to realize what some of it means. Now, for me, that suggests a data structure resize. I've seen that sort of pattern before, so I want to instrument the code and look for resize operations of data structures. A really good tool for this in Java is btrace. And I can write a btrace script looking for resize operation called on things like hash maps. So we run the code again through the tests with this instrumentation in place, and guess what? We had resize operations happening at the same time as we started seeing these effects. We were able to correlate them and realize that's what was going on. So we were able to then pre-size data structures or swap data structures with others to grow in a more predictable fashion rather than growing in jumps like this, so we get the right behavior that we needed. We also sort of discovered that these gaps where you're processing nothing, that turned out to be GC. And what was interesting was we hit a GC point here. Some of the resizing was going on because of other effects. We ended up having another GC event at the end so close because you actually had to copy all of the data across from one data structure to another. And so you can start to see a lot of what's going on in your system. And whenever this is happening, you're back to that, if you don't meet your response time guarantees, what is the implication of that? Well, the implication in these sorts of systems is you end up losing money. It's not like the goalkeeper scenario where people die because the ship gets blown up, but we end up losing money. But it could also be a case of we have pissed off users who are just not happy that all of a sudden the system's gone away for a while whilst it's been sorted out by housekeeping. It shouldn't be behaving like this. So we resized all of the data structures and we replaced some of them with better data structures in how they grow and behaved, and we ended up with this graph. So again, we're going faster, but look, there's really interesting effects here. Like I find these like strata coming in. Like I've seen this a lot before, and that usually screams out to me is migrations of threads around different cores. So on our multi-core boxes, the scheduler will move our threads around. And the problem is when you move from one core to another core, you end up with a cache that's cold. You have to rewarm that cache before you're running fast again, and so you run slow for a while before running fast. Like how can we track that? Well, we start tracking things like context switches in the kernel, looking at thread migrations around. We can get counters for all of this. So we realized that's what was going on. We were getting much more thread migration than we expected. Well, how do we stop that? Well, we looked at pinning threads to particular cores. And people go, that's a crazy thing. Why would you want to pin threads to cores? It's a really bad idea. That's what happened when we pinned the threads to the cores. We tightened that all up and we got a bit faster. So for certain classes of application, you do want to constrain threads to cores. And going back to that whole thing about it being fractal and working at different levels, so if I'm doing close to hard real-time trading systems and I want to work in sort of single or a few tens of microseconds response time, I will want to pin threads to cores. I will want to isolate cores. I will want to make sure interrupts go to certain cores and how it behaves. But if I've got a larger application that's doing things like just normal web traffic, I mightn't want to go to that extent, but what I probably do want to do is isolate an application onto a socket in a NUMA machine so that you're not crossing all of the interconnects inside our boxes, because these machines now are effectively distributed systems, and there'll be more on that in a second. So what are the pitfalls? You're digging along under the latrine, what's likely to get you? Well, let's start at the bottom and work our way up. Our processors have got lots that they're doing, but some of the motivations for the design is a bit different than many people expect. One of the primary motivations people have now is energy saving. We want to save power. We don't want huge bills in our data center. We don't want to run batteries down, all of these sorts of things. So much of the design is going into energy saving. Well, to achieve the energy saving, they switch off different parts of these CPUs. And once you need to do something quickly, they have to be switched on again. This takes time to respond. So if you're at a really responsive application, you don't want it going down into these sleepy states. So P states, C states, these are useful things that you've got to be aware of. Well, how do you change some of those? Well, quite often you change them in the BIOS. So you go in, you set that in the BIOS, but guess what? If you use something like Red Hat, you set it in the BIOS, Red Hat boots up, and then it goes, oh, what's this set to? No, I'm going to switch it back on again, even though you switched it off in the BIOS. So you have to then configure stuff in the operating system to sort of get this right. We've also got things like Turbo Boost, Hyperthread, all sorts of interesting complications in there. But it's even getting weirder than that. You'll hear about things like AMT or vPro, some of these different bits of technology where these CPUs can be controlled now, controlled by a power line or by the network line. So what are they doing? Well, effectively gathering data and sending it to the NSA. This is the sort of stuff starting to happen now in our CPUs. You'd be surprised what's happening at a low level, and you need to be able to control some of this to make your systems responsive. So let's come up a level. I mentioned these things are distributed systems. So our cores are sitting inside sockets. And so you get multiple sockets in a core. They've got local private caches. They've got shared caches within the socket. But interestingly, these sockets are connected together by quick path interfaces. These are networks on chip now. The L3 caches sit on ring buses. These are like our token ring networks we used to have for years ago for connecting our machines. Within the chip, they're doing these sorts of things. This fractal behavior is happening again. And memory now is directly connected to each of these sockets. So if you're dealing with the memory on one socket, but your cores are running on another socket, you're having to cross that quick path interface. You're making a remote call effectively. And that's where sometimes you want to bind your application. So if your application can completely fit within the memory and CPU usage here, you should do that because you don't want to be taking the cost of going across there. It's distributing for no need. So the patterns that you use in a data center apply equally in this. This is one thing I find completely bonkers, is why people think that they're programmed differently on a machine than they do across machines. It's actually the same problem. We should be thinking the same way. And as the world moves forward, we are not going to get better on latency. Latency has been restricted by speed of light. We are getting much, much more bandwidth. We need to have shared nothing, and we need to be communicating asynchronously for this to happen, even on the same machine. That's the way you've got to start thinking. And you start thinking like that, you've got the same programming model. It works local and works remote. So we come up from that, and we use our operating systems, and we get into the wonderful world of virtual memory. Like we're used to garbage collectors pausing, for example, like our .NET garbage collector or Java garbage collectors, they pause and our applications don't respond. Well, guess what? Linux does a lot of like garbage collection type activities. And whenever it's doing those, it's paused and it's not responding. Like start looking for things like transparent huge pages, the min-free memory, how swap works. Why do we need swap today? Most applications I see have way more physical memory than is actually needed. So why would you have swap turned on a machine? Like a lot of this comes from a past whereby we wanted much larger address spaces than we had physical memory. That world's flipped. In fact, there's probably a good argument now for why we should start considering not using virtual memory. We should be just using physical memory for our addressing because it would make things a lot simpler and we could go faster in how we run. So things are changing and we need to be aware of this. We get up into our JVMs. Safepoints. I think some JVM engineers should have huge fines for any time they introduce a SafePoint to code. So what is a SafePoint? Well, there's certain operations our VMs do, and when they do them, they want to have a nice, simple world. They don't want other threads mutating structures or doing stuff when they could to perform that operation. So what they have to do is they've got to bring all those threads to Safepoint. So they stop the world, they make the changes they want to make, and then they can start the world up again. Well, things like garbage collection typically runs like that for most of our VMs, but also things like bias locking when that gets revoked, some de-optimization, taking a stack trace, some of these things that we end up doing, they cause all of our threads to come to Safepoint, and they cause pauses. Now, going back to Amdahl's law, bringing all of those threads to Safepoint, guess what? That's a sequential component in your algorithm, and everything's going to bottleneck and choke on it. So if you have lots of these in your code, you're going to really restrict throughput. I've seen machines that can't get over sort of 60, 70% utilization, bringing threads to Safepoint because it's allocating too much or revoking locks or de-optimizing, all sorts of weird things inside Hotspot. So just being aware of some of this stuff was really helpful. Even better, let's encourage our VM designers to not do a lot of this stuff. Virtualization. We all are running on machines typically these days that are virtualized, but it's a huge tax, especially for things like I/O or going to disk and things. People say virtualization adds a small amount. That is not my experience. From measuring lots of systems, virtualization adds a lot. And it adds an awful lot, especially when it's badly configured. And many people don't spend any time configuring their base systems. They don't configure where interrupts go. They don't configure how the network stack works, especially in these virtualized environments with software switches. And there's so much performance gets left on the table because of this. I think it's actually a fundamental problem is that we have the ops people who support the systems, and we have developers who write code, and neither the two of them really work together. We talk about DevOps and stuff and all, but even the DevOps folk don't really know how to tune a network stack properly. They don't know where interrupts should go. They don't understand the hardware very well. All they've got is a bit of root access and to script some stuff up to get it out to live. Yes, that's a nice step forward, but we need to go further than that. We need to be working together to do this much better. Classic case I keep seeing of where you get lots of pauses in applications, and it can be nasty, is we have code, and we have locks, and we have to notify another thread that something's done. Like, I put something onto a queue, another thread's waiting to take something off a queue, it has to be notified that something's there. This is a kind of classic problem. You see it in all sorts of spaces. So we use wait notify, we use signal await, whatever combination we do. See, as soon as you do this sort of thing in your code, you just start playing roulette with your latency. And I've seen anything from tens of microseconds up to milliseconds and seconds before an application starts responding properly again because of scheduling effects that's going on with this. In fact, you can see applications that are spending such a huge amount of time scheduling. You're running things like VM-stat, and you look at the threads that want to run, and they're all waiting on some of this stuff going on. It's absolutely crazy. We need better ways of doing that, and there are better ways. But fundamentally, don't share some of this data and don't have to hand off this way in the first place. Abstractions is a fascinating one. We keep talking about abstractions. Like Dijkstra described abstractions as being more precise. We need to be getting much more precise in how we deal with stuff. I mean, this is the kind of interesting flip one. It was Spolsky's talking about how they're leaky. Well, this is because you got them wrong. That's why abstractions end up being leaky, because they're wrong in how we do it. We need to understand what's going on. And this whole sort of thing about frameworks and ways of infacting our code, it's just crazy, and this causes a lot of these abstractions to go wrong because we cannot ignore some of the detail of what's going on. Like, you can ignore certain levels of detail if it obeys an abstraction. You cannot ignore detail if it doesn't obey the underlying abstraction. And this becomes very important in how our networking and our code. So going back to reminding again what Dijkstra said to us about what abstraction is, the thing is we have to be more precise when we add an abstraction. It's not a case of wishy-washy hiding stuff behind a strange interface that doesn't give us a true representation of what's going on. I like to call this mechanical sympathy. And I think it's a useful thing to know how things work underneath. You don't need to know how to build it or rework it, but you need to know what it gives you. Like when you drive your car, you don't just have a number of pedals. Here's the loud pedal, here's the stop pedal, and if you happen to have a stick shift, what's this other one do? Is it somewhere to rest your foot? But no, you need to know a little bit more about what's going on, otherwise you don't get the best out of it. Classic one we keep seeing is systems respond really well, except in the presence of failure. If there's anybody who remembers the Monty Python, the Black Knight, it's only a flesh wound. You keep going. Most interesting systems are constantly in a state of something being broken. You must be able to continue all of the time. There is no such thing as perfect health in any significant system, so learn to cope with it and just keep going. This needs to be a normal thing. So let's look at some algorithms and techniques to deal with this and how we go forward. Kind of first up, I would say, like, if you're doing science, you need to be doing clean experiments. So if I was a chemist and I'm going to do any chemical experiment, if I use dirty test tubes, I'm not going to get a good result. I'm going to get some random result that's not repeatable science. It's not a repeatable experiment. Well, in software, we need to be doing the same. We need to clean up the experiments that we're doing so that we have meaningful data coming out of it. And from a performance perspective, there's lots of things we have to fix. We have to make sure we have sufficient CPUs to run things. I keep seeing people trying to run examples of tests and don't know how many CPU cores they actually need to run for the number of steps that need to happen in parallel. That's crazy. We need to do that. We need to turn off some of those effects, like PCs switching themselves into low power states and then coming out of them. You end up measuring that rather than the test you actually want to have. So there's lots of stuff here. You can kind of go and Google for some of it. I'm not going to spend a lot of time on it. One thing I will point out, and hopefully Gil will go into more detail tomorrow, is J-hiccup. If you're going to do all of these tests, you want to make sure you're running on a nice, clean, quiet machine. And one of the best ways to do that is running this little tool. And what it does is it just runs in the background and sees if a thread can wake up on a regular cycle. And if it can't wake up on the regular cycle, something happened. Something was going on that it wasn't able to run, so your machine wasn't clean. There's some cron jobs going, there's some defragmentation going on, there's some swapping, whatever it happened to be. This will start telling you don't have a clean machine. You need to do that. And you need to tune things that are underneath it so you've got this clean environment and get that mechanical sympathy right. We then should be profiling our applications. And guess what? Most profilers you use lie. Many people don't realize this. So things like YourKit, like JProfiler, some of those profilers, JVisual VM, they profile at what is called Safepoint, which I mentioned earlier. Those Safepoints is they wait till the code reaches Safepoint, then they do stack sampling at that point to see, guess what? Those Safepoints aren't in your hot code. They don't show you where the real things are. There are profilers that can do this for you. So typically those were things like Intel vTune, Solaris Performance Studio Analyzer. These are kind of complicated, difficult tools to use. The nice thing now is we have Flight Recorder in Mission Control that's available with Java 8. And this is really nice in that we can, in development, profile our applications. If you are willing to pay Oracle for the commercial license, you can even profile in production. And it doesn't cost that much to do your profiling. So that's one example of how to do this. Other VMs like the Zool, Zing VM does this sort of thing too. We can get real profiling information and find out where the time's actually spent. I recommend you do this as a regular thing, not even if you want to go fast. Because when you start to understand your code, it works really well if you can build up mental images that are reinforced from multiple perspectives. So write your tests, write the code, run through it in a debugger. You run through it in the debugger, it becomes dynamic. You can see step by step. You can see branches being taken, how many times you go around loops. You start seeing, oh, I never go that way through the code. My tests don't cover that. That helps build up your mental picture. It improves it. It's the same thing with a profiler. You get a feel for costs. You see where all the costs lie in your system, and it becomes quite a strong mental model. This actually, I find, makes people faster at development because they understand the code from many different perspectives, and it works well. So make this common. It's also really good for the days when things go wrong. If you're using a debugger every day, you're using a profiler every day, whenever things go wrong in production, it's muscle memory. It's not the, oh no, how do I use a remote debugger to connect to something to find out what's going on? How do I profile? Where do I find these features? That should just be instinctive and natural because you should just be using it all the time, and it doesn't take much time. It's also really useful to incorporate telemetry into your systems and capture things in histograms and counters and gauges, these other sorts of things. We should be building telemetry in from the start. It tells us how our systems are performing. It also helps us with tuning, debugging, dealing with them. Don't use your users to provide you telemetry. That's a really bad experience. Like, you should know things are going wrong before your users know they're going wrong and be able to act on it and plan. Useful technique I find a lot, I call this smart batching. Todd Montgomery pointed out to me recently that a better name would probably be natural batching for how it works. Most people, when they use batching, they misunderstand batching. They get the wrong kind of feel for it because it feels like a bad thing. You shouldn't do batching based upon timeout. You should be doing batching based upon a means of pulling things in as naturally and as quickly as you can. I'll show you an example of that in a second. But if you do batch well, this is what you can do to latency in your applications and response time is your typical application will follow the queuing theory and go up the J-curve. The blue line is possible when you design using batching techniques. So what would be a typical batching technique for this? So let's say I had 3 producers and they want to use a resource that's contended. If they go to use that resource in a contended fashion, it needs to be protected by some form of mutual exclusion. Put a lock around it, whatever that happens to be. Now, if I go to use that, if you look at the units of time to use that, so if it's 1 unit of time, one thread gets to use it in 1 unit of time, the next thread gets to use it in 2 units of time, and the third one gets to use it in 3 units of time. You've got an average of 2 units of time. Like, expand that up to be 10 things, you've got an average of 5 units of time for waiting that. And you've also got a big distribution, so your responsiveness is not as predictable and normal. Well, let's change this a bit. Start thinking asynchronous. Let's start using this in a batching scenario. So rather than using the resource directly, you enqueue your request for that resource, and you have a batching thread that drains that queue as fast as it can. So the worst case scenario is it goes to the queue, pulls one thing off it, and writes it down to the resource. You then go back again, you pull 9 things off it, and you write it down again. Look what you've done to the mean response time in that case is your average now is less than 2, as opposed to being 5. And the utilization of the underlying resource is much better. So these are kind of old, boring techniques that actually work really well. We don't seem to have these as part of our normal toolkit when we're building many applications. So let's bring some of this back. So we need to amortize those expensive costs. So also now, if I'm going asynchronous and I'm dealing with all of these precious resources in this way, the best thing I can do is put queues in front of everything. Now, doing the telemetry side, these queues can become first class. I can track flow rates. I can track how long they are at any given point in time. I know a lot about my system, but more importantly, I can apply backpressure. Because ultimately, to meet a response time guarantee, I want to make sure I don't overutilize any resource and I don't want to queue too much. If you use unbounded queues, that's where you go right up the J-curve. You bound your queues and it won't be quite as bad. But what's going to happen when those queues fill? Well, you apply backpressure in your transaction service, you may apply backpressure in your gateways, and eventually you apply backpressure to your customers. What's that look like? Say it's a web request is coming in. We need to return a 503, server busy. That is much better than taking in another request, overloading your system, eventually probably running out of memory and crashing. Go as fast as you possibly can, offer the best service you possibly can, and then the worst case scenario is you say, I'm too busy, come back later. Or if you designed your client quite well, as your client goes to another service, because you've actually distributed your load, you can do this in a much better way. So bound these queues, that lets you meet your response time guarantees. Blocking designs, it's a really insidious problem that we have in our industry. And I like to think of it as like, let's stop getting in our own way. Let's start going asynchronous, start using things in the right way. So we start using our networks, we start using our disks, all of those sorts of things. By going non-blocking, we can take those approaches like putting smart batching in front of something, applying all of the right levels of backpressure. If we just use things synchronous, we end up queuing, but uncontrolled queuing, because guess what? If you put a lock around something, you have a queue. And it's a queue that you don't control and you don't monitor, because as I take the lock, other things that go to take the lock, they get put on a queue to use it again later. So queues are everywhere. You cannot escape them. Let's not use a lot of these synchronous techniques because they start off looking really good and then it goes horribly wrong. I like to think of synchronous programming as the crystal meth of programming. It starts off reasonably good. You think you're making great progress, but very, very soon, you're just a mess. And just things do not work. We need to get over this. We need to just leave the synchronous programming mentality and accept that everything is asynchronous, and that's how the world is. So when we're going asynchronous, we can start using things like lock-free algorithms. And this all comes down to basically protocols of interaction. We need to get used to this way of, rather than having central control, we agree protocols of interaction. Those protocols then let us do things in a nice way. So anybody can remember from going to college and you had to have your room shared with roommates, leave the tie on the door? It's a simple protocol. You don't need to have a controlled way of doing stuff. So start thinking of that. We can beat the notify problem by doing this. Now, once I've got all of these things, what I should be doing is making them observable. So I should be having state machines describing these asynchronous systems. And this is a rather horrible TCP state machine, but I'm not trying to make a point out of this state machine itself, but other than the fact that state machines themselves should be observable, because if I make them observable, it makes monitoring so much easier. So for example, I take an order, I submit something off to another system to get it verified. I just go to a different state in the state machine. And if I can observe those state machines, if this thing doesn't get dealt with later, something else can take an action. I can see progress at all times. Make your system transparent. Make these things observable. Don't have them hidden. How do I stay responsive in the case of failure? Well, one of the things that we can do quite simply is, if we've got requests coming from lots of clients, if we can sequence those requests, we can send them to many instances of a service. And guess what? The services can respond at whatever rate they want. As long as those messages are idempotent and we can track that we have seen a message before, they can both respond, and actually the first to respond wins. Nice and simple. If one of them died, it doesn't matter. The system just works. What's really cool with a lot of these sorts of designs is if one of these systems takes a GC pause or decides to just stop responding for a little bit of time and then come back again later, the system is still responsive. It still works really well. And even better than that, we can replicate the models and build them many times on other machines, because then we can answer lots of queries and we can deal with them in lots of other ways. So just simplifying a lot of this down and don't have all the contention in the data, making these things deterministic, makes our life much better. So now, kind of coming up quickly in closing, we're in an interesting world. There is something coming. Is it winter? Are we in the north? It's actually quite warm here, so it's not too bad. What is actually happening is the Internet of Things. Last year was the first time we passed the point where we had more devices connected to the Internet than we have humans on the planet. And that is only going one way. Depending on how you view the world, there's going to be anywhere between 20 and 75 billion devices connected by 2020. It doesn't matter what number is correct. The one thing that is clear is there's lots of them. So what that means is we cannot control the arrival rates to our systems. We want our systems to be responsive. We can't control those. In fact, we want those high arrival rates to happen. So we need to start thinking about how we improve our service time. Our service time is key to keeping our systems responsive and making that work well. Because if we don't sort the service times, the only other thing we've got is to go parallel. And if we go parallel, we have to make sure we have no contention, because actually solving the contention problem is really, really hard. And we just don't want to get too tied up into that. And on that point, I'm going to leave you, and I think I'm just about out of time.